Look up at the moon tonight, and understand that what you're seeing is only half the story. Because for millions of years, Earth didn't have one moon. It had two. And the second one crashed directly into the first. What came out of that collision reshaped everything we knew about why life on Earth is even possible. Now, I know what some of you are already thinking. Is this one of those clickbait space videos? Fair. I would be thinking the same thing. But stay with me for just 2 minutes. What we're going to get into today is one of the most legitimately mind-bending chapters in Earth's entire 4.5 billion year history. And it's backed by real science, peer-reviewed, published in Nature, and gaining ground every year as new evidence comes in. So, let's go. We need to start with what you already know. Or think you know. The moon. It hangs up there, 384,400 kilometers away, completing a full orbit around Earth every 27.3 days, with gravity 1/6 of what you feel right now standing on the ground. It's been there for approximately 4.51 billion years. You learned this somewhere: school, a documentary, a late-night Wikipedia spiral. The basic story goes like this. Early in Earth's history, a Mars-sized body called Theia crashed into proto-Earth, blasted an enormous cloud of debris into orbit, and that debris slowly coalesced into the moon. The giant impact hypothesis. Solid science. Widely accepted. And that version of the story is true. It just isn't complete. Here's what nobody really talks about when they explain the moon, and this is the detail that I want you to hold on to for the next hour, because everything else we discuss today hangs on it. The moon has two sides. An obvious statement. But those two sides are extraordinarily, profoundly different from each other. The side we see, the near side, is covered in what geologists call Maria. Dark, flat, volcanic plains. About 31% of the near side is blanketed in this ancient basaltic rock. It's what gives the moon its face, the man in the moon pattern that every human civilization has looked up at and found shapes in. Now flip the moon over. The far side, the side that you, me, and every single human being who has ever lived on this planet has never seen with their own eyes, not once, not even once in all of recorded history, looks completely different. It's almost entirely covered in cratered highlands. Pale, ancient, battered. The volcanic Maria that dominate our view of the moon. Less than 2% coverage on the far side. You know, when I first started looking into this, I went down a rabbit hole about the simple fact that humans have only ever seen one face of the moon. Every ancient Greek astronomer, every Babylonian stargazer, every person who has stood outside on a clear night for the past 100,000 years, same face. Always. The far side remained photographically unknown until 1959, when the Soviet spacecraft Luna 3 looped around and sent back the first grainy images. And what scientists saw was not what anyone expected. It wasn't a mirror of the near side. It was, geologically speaking, a completely different world. And here's the number that really nails this down: the moon's crust on the near side is roughly 60 kilometers thick. On the far side, about 100 kilometers thick. That's a 40-kilometer difference in crustal thickness between two hemispheres of the same object. For decades, this asymmetry sat there like an unanswered question, humming quietly underneath all of our moon science. So we have this ancient, asymmetrical, silent companion, one we've stared at our entire existence without truly understanding. And in 2011, a pair of researchers at the University of California, Santa Cruz published a paper that changed the conversation entirely. It started with a question almost no one had thought to ask: what if there used to be two of them? The answer they found wasn't just surprising. It was the key to explaining why the moon looks the way it does, and, as we'll discover, why Earth looks the way it does. We'll get there. But first, we need to go back. Way back. To a time when the solar system itself was still figuring things out. The early solar system was not the orderly, clockwork system we observe today. If you could somehow stand outside it 4.5 billion years ago and watch, which, to be fair, would immediately kill you in about 40 different ways, what you would see is not a solar system. It's a demolition derby. Objects the size of small countries, medium-sized countries, sometimes entire continents, all of them moving through space at 20 to 30 kilometers per second, colliding, merging, shattering, and starting the whole cycle again. To give you a sense of that speed, at 30 kilometers per second, you travel from New York to Los Angeles in roughly 3 minutes. These were not gentle interactions. This period, specifically between about 4.1 and 3.8 billion years ago, is called the Late Heavy Bombardment. The inner solar system was being carpet-bombed. The lunar craters you can see with a basic backyard telescope. Those are scars from this era. They are physical evidence, visible to the naked eye on a clear night, of an unimaginably violent chapter in our cosmic neighborhood's history. And planets don't form before this chaos, they form through it. The process is called accretion. Dust and gas clump into pebbles. Pebbles collide into rocks. Rocks smash into boulders. Boulders accumulate into planetesimals. Planetesimals crash into each other and, sometimes, stick. Building a planet is less like construction and more like a wreck. You're not adding pieces carefully. You're surviving collisions until you've absorbed enough mass that your gravity does the absorbing for you. There's also what's called the Grand Tack hypothesis, which proposes that Jupiter, the solar system's gravitational giant, may have migrated inward early in its history, then back outward again. If that happened, it would have flung enormous quantities of debris into the inner solar system's orbital paths like a bowling ball rolling through a crowded room. This would make the bombardment of the early inner planets not just plausible but essentially inevitable. I want to pause here for a moment because I think we lose sight of something important. When we say, the early solar system was chaotic, that phrase doesn't really land the way it should. There was no peaceful beginning. There was no gentle cosmic dawn. The Earth we stand on today is, at its core, made of the wreckage of collisions. You and I, every atom in these bodies, came from debris. From destruction. From impacts that released energies so far beyond any human reference point that our language genuinely struggles to contain the description. I find that weirdly profound every time I come back to it. Now, the original giant impact. Theia. A body approximately the size of Mars, moving through the early solar system, and on a collision course with Proto-Earth roughly 4.5 billion years ago. The energy released in that impact is essentially impossible to visualize. It liquefied Earth's surface. Temperatures reached somewhere between 1,200 and 2,200 degrees Celsius across what we would one day call home. The Earth day at that point, after the spin-up from the impact, was approximately 5 to 6 hours long. Most of Theia was absorbed into Earth, but a ring of vaporized and molten debris was thrown into orbit. Over millions of years, that ring coalesced into the Moon. So the Moon was born from violence. That much we've known for decades. What we didn't know was that the violence wasn't over yet. After the primary Moon formed, the system, you might think, would have started to stabilize. And in a broad sense, it did. But the debris field from the Theia impact was not clean. It was not precise. And the laws of orbital mechanics, it turns out, had one more trick to play. A second object formed in orbit around Earth. Not a fragment. Not an asteroid. A second moon, and it settled into a position that allowed it to hide, in a sense, in plain gravitational sight, for tens of millions of years. What formed in those first million years, and how it managed to stay hidden in orbit for so long, is where this story gets genuinely strange. The leading scientific model for the second moon was published by Eric Asfog and Martin Jutzi in the journal Nature in 2011. Their proposal, the Theia impact, created not one moon, but two. A large primary moon, and a smaller companion approximately one-third its current size, roughly 1,200 kilometers in diameter. To put that in perspective, that's roughly the size of Ceres, the largest object in the asteroid belt. This wasn't a pebble. It was a geologically substantial body in its own right. Both moons orbited Earth for tens of millions of years. The mechanism that made this possible is called a Lagrange point. Every two-body gravitational system, a planet and a moon, for example, has 5 specific locations in space where a third, smaller object can sit in gravitational equilibrium, neither falling inward nor flying outward. These points are labeled L1 through L5. The most stable are L4 and L5, which sit 60 degrees ahead of and behind the secondary body in its orbit around the primary. The second moon, in Asfog and Jutzi's model, parked itself in either Earth's L4 or L5 Lagrange point, riding in the moon's orbital path at a stable 60-degree offset. This is not a theoretical abstraction. Jupiter right now has thousands of objects called Trojan asteroids, some of them hundreds of kilometers across, parked in its L4 and L5 Lagrange points. They've been there for billions of years. The same gravitational physics that keeps Jupiter's Trojans in place is what kept Earth's second moon stable for tens of millions of years. This happens. It is happening right now, elsewhere in this solar system. It's not exotic. It's orbital mechanics. The second moon would have been rocky, heavily cratered, and, relatively quickly, tidally locked to Earth, meaning one face would have always pointed toward us, just as our current moon always presents the same face. Its surface would have been airless, cold, geologically quiet after its initial cooling period. But its gravitational influence would have been felt. From Earth's surface in that era, if you can imagine any vantage point on a largely molten, geologically violent proto-Earth, the night sky would have held 2 moons. One large and bright, one smaller, moving on its own slightly different path across the sky. The tidal patterns in any early ocean would have been complex, influenced by 2 separate gravitational sources pulling from different positions. Now, I want to be upfront about something here, because I think intellectual honesty matters more than a clean narrative. This is a hypothesis. A very well-supported one, but a hypothesis. We don't have a physical sample of the second moon sitting in a laboratory. What we have is a model that explains something that nothing else could explain cleanly. And in science, that matters enormously. When a theory solves a mystery that had no other satisfying solution, you pay close attention. The two-moon theory doesn't just explain one anomaly, it explains several, simultaneously, with a single mechanism. That's the kind of explanatory power that makes scientists take notice. Asfog and Jutzi estimated the second moon's mass at roughly 4% of the current moon's mass. Computer simulations suggest the two-moon system could have remained stable for anywhere from 10 to 100 million years. 10 million years is a long time, long enough for both moons to develop distinct geological characters, to fully cool, to establish their separate identities as bodies in the solar system. And then, it ended. The second moon began to drift. Slowly at first, almost imperceptibly. But gravity doesn't forget. And over hundreds of thousands of years, the smaller moon crept closer and closer to the one we know. Until there was nowhere left to go. The collision that ended the two-moon era was not the kind of impact Hollywood would depict. There was no blinding flash of light visible from across the solar system, no explosive shockwave, no dramatic shatter into 1,000 pieces. What happened was something that almost defies intuition, a slow-motion catastrophe that unfolded over timescales so vast that the word slow loses its meaning. Here's the mechanism. Lagrange points are stable, but not unconditionally stable. Gravitational perturbations, tiny nudges from Jupiter, Saturn, and other planets, accumulate over time. They're individually negligible. But over millions of years, those small nudges build into something that pushes an L4 or L5 object out of its equilibrium position. Once disturbed, the object begins to migrate. Not in a straight line, in a complex, elliptical drift governed by orbital mechanics. The second moon, after tens of millions of years of stability, began that drift. As it drew closer to the primary moon, tidal forces began to deform it. Imagine the shape of the smaller moon elongating slightly, stretching toward its larger companion as the gravitational gradient between near and far sides increased. This is the same fundamental process that turns comets into elongated, stretched shapes as they approach the Sun. Gravity doesn't just attract, it differentiates. It pulls harder on the near side than the far side, and over time, that difference reshapes. The relative velocity at the moment of impact was approximately 2 to 3 kilometers per second. That sounds fast, but in the context of cosmic collisions, it's slow, almost gentle. A typical asteroid strike on Earth involves impact velocities of 20 kilometers per second or more. This collision was, by comparison, a low-energy event. And that distinction is absolutely critical to understanding what happened next. A high-velocity collision between two moons would have been catastrophic and decisive, one or both objects shattering into debris, potentially forming a ring around Earth, potentially ejecting material into deep space. What a low-velocity collision produces is something entirely different. Think of it less like two billiard balls crashing together and more like two lumps of clay meeting. The smaller moon didn't bounce off. It didn't explode. According to computer simulations, it smeared, spreading its material across the surface of the larger moon like a slow, cosmic paintball impact. The technical classification for this type of event is a subcatastrophic accretion event. The smaller moon was absorbed. There's something almost elegiac about that, if you let yourself sit with it. A collision at low velocity doesn't end in an instant. It lingers. The smaller moon's material didn't simply strike the larger one, it joined it. It became it. The moon you look at tonight contains both original moons, fused together across billions of years, their boundary invisible to any telescope we currently possess. Current models suggest the approach phase, from Lagrange destabilization to final contact, may have taken anywhere from 100,000 to several million years. On a human timescale, incomprehensibly long. In geological time, essentially a heartbeat. The collision happened. The smaller moon ceased to exist as a separate body. Its material smeared across the far side of the primary moon, adding a thick layer of ancient crustal rock, anorthosite, to what had previously been a relatively uniform surface. And that specific detail is exactly what we see when we measure the far side's geology today. The evidence has been there the whole time. We just didn't know what we were looking at. But here's what really stopped me when I first understood this: the collision didn't just change the moon. The ripple effects of that ancient impact extended all the way to Earth. And when I say extended all the way to Earth, I mean they may have made it possible for you to be alive right now. Let me walk you through the actual geological evidence, because this is the section I think of as the CSI moment. We're going to read the crime scene. And the crime scene is the moon itself. Evidence Piece 2, the South Pole Aitken Basin. The largest confirmed impact basin in the entire solar system sits on the moon's far side. It is 2,500 kilometers wide and 8 kilometers deep. To put that in scale, it would stretch from New York to Los Angeles with room to spare in every direction. The basin exposes deep mantle material that should not be accessible at the surface, which tells us that something of extraordinary energy disturbed the far side's geology at a very early date. Some researchers argue this basin marks the initial contact zone of the two-moon merger. That debate is ongoing. What is not debated: the South Pole Aitken Basin represents one of the most energetic geological events in lunar history, concentrated on the far side, during the exact period the two-moon collision would have occurred. Evidence Piece 3, the near side's volcanic Maria. Here's where the asymmetry becomes a complete story rather than an isolated mystery. The near side's thin crust, 60 kilometers, offered far less resistance to magma rising from the moon's interior. Volcanic eruptions could break through. The far side's thick crust, the deposit from the two-moon collision, insulated the far side interior, suppressing volcanic activity. Result: ancient lava floods concentrated entirely on the near side, creating the dark Maria Plains, which created the face of the moon that every human civilization has ever seen. The man in the moon exists because two moons collided billions of years ago and deposited crustal material in precisely the configuration required to direct volcanic activity to one hemisphere. Aesthetics as a consequence of physics. Evidence Piece 4, computer simulations. When researchers model the early Earth-Moon system with two moons included, the simulation outputs consistently matched the observed geological asymmetry. Without the two-moon model, explaining the far side thickness required assumptions that satisfied almost nobody. The two-moon collision resolves multiple independent observations with one mechanism. Asfog's 2011 Nature paper states directly, the present hemispheric dichotomy of the moon may thus record the terminal accretion of a once-companion moon. That's as close to a smoking gun as planetary geology gets. I want to be clear, and this is something I genuinely wrestle with in these videos: this is not settled science in the way that the moon's orbital period is settled science. There are planetary scientists who favor different explanations for the asymmetry. Some argue for large-scale lava ocean crystallization dynamics. Some argue for a modified single-impact scenario with different fluid dynamics. The two-moon theory is the best current explanation. In my reading of the literature, it explains the most observations with the fewest additional assumptions. But best current explanation is not the same as proven fact, and science is honest about that distinction. We should be too. What the evidence does tell us, with confidence, is that something dramatic happened to the moon's far side very early in its history. Something that deposited thick, ancient crustal material. Something that redirected the entire subsequent geological evolution of the moon's two hemispheres. The two-moon collision model is, currently, the most coherent story that connects those dots. And I promised you earlier that this collision might be the reason you exist. That sounded dramatic. It wasn't an overclaim. To understand why, we need to talk about something that most people never connect to the moon: the stability of Earth's axial tilt. Earth is currently tilted 23.4 degrees relative to its orbital plane around the Sun. This tilt is what gives us seasons. The northern hemisphere tips toward the Sun in June, away from it in December. Crucially, that 23.4-degree tilt is stable. It wobbles slightly, between 22.1 and 24.5 degrees, over roughly 41,000-year cycles. But it doesn't swing wildly. It doesn't lurch from vertical to nearly horizontal over millions of years. It stays, within a narrow range, predictable. Mars has no large moon. Mars's axial tilt currently sits around 25 degrees, similar to Earth's. But over geological time, Mars's tilt has ranged from roughly 10 degrees to 60 degrees, driven by gravitational perturbations from the other planets with no large moon to dampen the wobble. Without stabilization, Mars's poles have, at various points in its history, faced almost directly toward the Sun, then tilted so far away that what are now polar ice caps were once tropical regions. The climate swings that produces are catastrophic for any hope of stable, evolving ecosystems. Theoretical models suggest that without our moon, Earth's axial tilt could vary between approximately 0 degrees and 85 degrees over tens of millions of years. 0 degrees means no seasons, the poles freeze permanently. 85 degrees means the poles are essentially aimed at the Sun for half the year, the Arctic Ocean boiling, the equatorial belt freezing. A planet oscillating between those extremes doesn't produce stable habitats. It produces a global climate that resets itself before anything complex can take hold. The Moon's gravitational influence acts as a gyroscopic stabilizer, its mass and orbital position damping the wobble that would otherwise send Earth's climate into that kind of chaos. More massive Moon equals stronger stabilizing effect. Here is where the two-moon collision becomes directly relevant to your existence. The merged Moon, the product of both original moons combining, is more massive than either of the two originals would have been alone. A system with two smaller moons in different orbital positions would have exerted a different, potentially less effective stabilizing influence on Earth's axial tilt. The collision that ended the two-moon era produced a single, larger stabilizer. And that may have been the precise configuration Earth needed. The tidal dimension adds another layer. The Moon drives Earth's ocean tides, and those tidal rhythms influenced the evolution of early life. Organisms in tidal zones, where the shoreline alternates between submerged and exposed, faced evolutionary pressures that drove adaptation. Wet and dry, submerged and air exposed, twice a day, generation after generation. Two separate moons would have created more complex, less regular tidal patterns. The merger into one larger moon produced simpler, more predictable tidal cycles, potentially more useful as an evolutionary driver. There's also the rotation question. The Moon's gravity is gradually slowing Earth's spin through tidal friction. 4 billion years ago, an Earth day was approximately 6 hours long. At that rotation rate, atmospheric circulation is faster, weather patterns are more violent, and surface conditions are more extreme. The Moon's tidal braking, slowing Earth toward the 24-hour day we experience now, stabilized the surface environment over billions of years. A single larger moon, post-collision, exerted this slowing force more efficiently than two smaller moons would have. I had one of those moments while researching this, the kind where you put your notes down and just sit with it. The idea that a collision between two moons, 4 billion years ago, in a solar system that was essentially still on fire, that specific event may have been a prerequisite for everything that followed. For every living thing. For every human who has ever existed. I don't have a word that fully captures what that feels like. Humbling is in the right neighborhood, but it doesn't quite reach. The merger of two moons may have given Earth the gravitational ballast it needed to maintain the climate stability that allowed multicellular life, and eventually, us, to evolve. Which raises a question that I find almost unbearably interesting: how common is this? Are there other planets, right now, circling other stars, with two moons that haven't had their collision yet? And what do those worlds look like? Multiple moon systems are not rare in our solar system. They are the norm. Earth's current single moon status is, among the larger planets, the exception. Understanding what those multi-moon systems look like gives us something remarkable, a living laboratory for what Earth went through. Jupiter has 95 confirmed moons as of 2023. The four largest, Io, Europa, Ganymede, and Callisto, are called the Galilean moons, and their gravitational interactions with each other are extraordinary. Their orbits are locked in a 1:2:4 resonance. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. This mathematical lockstep is the direct result of their mutual gravitational tugging over billions of years. Io, the innermost, is the most volcanically active body in the solar system, not because of Jupiter's gravity alone, but because of the combined tidal squeezing it receives from Jupiter and the other Galilean moons simultaneously. It's a world in perpetual geological crisis, driven by the interactions of its neighbors. Jupiter's moon system is a scaled-up version of what Earth's multi-moon system might have looked like if the collision had never happened, multiple moons pulling at each other and at the planet, creating extraordinary tidal and geological activity. The difference is that Jupiter's system has maintained this configuration. Earth's did not. Mars offers something even more instructive. Phobos, Mars's inner moon, is currently spiraling inward at approximately 1.8 centimeters per year. In around 50 million years, Phobos will either collide with Mars or, more likely, be torn apart by tidal forces before it gets close enough to impact, disintegrating into a thin ring around the planet. Right now, Mars is experiencing its own slow-motion moon catastrophe, an orbital decay playing out in real time, a process analogous to what Earth's second moon experienced billions of years ago. We are watching it happen. Deimos, Mars's outer moon, is gradually moving outward and may eventually escape Mars's gravity entirely. Meanwhile, Mars has no large stabilizing moon, chaotic axial tilt, and no climate stability. The connection is direct. Saturn's rings, viewed through this lens, become even more striking. Those iconic bands are believed to be the remnants of a moon, or moons, that were either shattered by tidal forces or disrupted during orbital evolution, their material spreading into a ring rather than consolidating into a single body. When you look at Saturn's rings, you might be looking at a moon that didn't survive. A different outcome, not merger, but disintegration. The universe offers multiple endings to the same story. While I was putting this video together, I found myself completely sidetracked for about 2 hours reading about Pluto and Charon, which is technically a binary system rather than a planet and a moon. Charon is so large relative to Pluto that both objects orbit a point in open space between them, not around Pluto's center. They are tidally locked to each other, each one always presenting the same face to the other. From the surface of Pluto, Charon hangs motionless in the sky, never rising, never setting. Two worlds in a permanent gravitational dance, each filling the other's sky. I found that image stayed with me for days. I'll probably make a video about it at some point. But that's a tangent. The James Webb Space Telescope is now detecting atmospheric signatures of exoplanets in the habitable zones of other stars. If the two-moon collision theory is correct, if multi-moon systems routinely progress toward destabilization and merger, then we might expect to find exoplanets with irregular climate signals, atmospheric composition suggesting chaotic axial wobble, temperature variations inconsistent with stable seasons. A planet whose moons haven't collided yet might be detectable, in principle, by the climate instability that multi-moon gravitational complexity produces. This gives the two-moon theory an observational frontier extending far beyond our own solar system. Multiple moon systems are everywhere in our cosmic neighborhood. And what we observe in them, gravitational resonances, tidal heating, orbital decay, the slow approach of one body toward another, these are all processes that Earth went through. What may be special about Earth's version of the story is how it ended, and what that specific ending set in motion. But here's where the story takes one final, extraordinary turn. Because the two-moon collision didn't just change the moon. It may have shaped Earth's interior. And the evidence for that, sitting deep inside the planet beneath your feet right now, is one of the most unexpected findings in all of planetary science. Deep inside Earth, beneath the mantle, at the boundary between the lower mantle and the outer core, nearly 3,000 kilometers below the surface, there are two enormous structures that geophysicists have been puzzling over for decades. They are roughly continent-sized. They are detectable only because seismic waves from earthquakes, shear waves, specifically, pass through them more slowly than through the surrounding mantle. This behavior gave them their technical name, Large Low Shear Velocity Provinces. LLSVPs. One sits beneath Africa. The other sits beneath the Pacific Ocean. For years, the standard assumption was that these structures were ancient, dense accumulations of subducted oceanic crust, tectonic plates that had sunk to the bottom of the mantle over billions of years and piled up. That explanation was workable, but it never fully satisfied. The structures are too large, too compositionally distinct, and too long-lived to fit neatly into that picture. Then, in 2023, a paper published in Nature by Qian Yuan and colleagues at Caltech proposed something that sent shockwaves through the planetary science community. These structures, they argued, might be the preserved remnants of Theia, the original impactor that created the Moon. When Theia collided with Proto-Earth 4.5 billion years ago, most of Theia was absorbed. But a portion of Theia's mantle material, denser and compositionally distinct from Earth's own rock, sank to the bottom of Earth's mantle and stayed there. It didn't mix. It didn't assimilate. It has been sitting at the base of Earth's mantle for 4.5 billion years, detectable today because it slows seismic waves in a way that Earth's native rock does not. Each LLSVP is roughly 1% of Earth's entire mantle mass. The seismic anomaly they produce is measurable by global networks of seismographs that track earthquake waves passing through Earth's deep interior. The compositional modeling in the 2023 paper suggests the LLSVPs are up to 4% denser than the surrounding mantle, consistent with a foreign body origin, a chemical signature distinct from the rock that formed Earth from the primordial solar nebula. Now connect this to the two-moon story. If Earth contains preserved remnants of the Theia impact in its deep mantle, and the Moon formed from the same Theia debris cloud, then the Moon and the LLSVPs share an origin. They are cousins, separated at birth, debris that went up and formed the Moon, and debris that went down and sank to the bottom of the mantle. And the second Moon, which formed from the same debris field as the primary Moon and was later absorbed into it, adds one more layer. The Moon you see tonight is a fusion of the primary Moon, Theia's ejecta, and the material of a lost companion moon. Three ancient bodies, connected by a chain of violence stretching back to the solar system's infancy, all present in some form in the world you inhabit. The Earth beneath you is not just rock. It is preserved history. Pieces of another planet, swallowed and stored for 4.5 billion years, still distinguishable from Earth's own mantle by their seismic fingerprint. The planet we live on is a palimpsest, layers of old worlds, written one on top of the other, never fully erased. Here is the sentence I want you to be able to carry with you. Earth's two-moon system ended when the smaller moon collided with the larger one at low velocity, depositing crustal material on the lunar far side, explaining the geological asymmetry we observe today, while simultaneously contributing to the moon's increased mass. which stabilized Earth's axial tilt and enabled the climate conditions necessary for complex life. And we may have evidence of the original impactor that started this whole chain preserved in Earth's deep mantle, detectable by seismic wave analysis today. In my completely biased opinion, that is one of the most extraordinary sentences in all of science. I'll be honest with you. When I read the 2023 LLSVP paper, at about 11 p.m., which was probably a mistake, I genuinely felt something shift. Like the planet I was sitting on suddenly felt different. More ancient. More layered. More alive with history. I'm not sure that makes scientific sense. But I think that's why I make these videos. Because occasionally, science hands you a moment like that. And I want to pass it on. Now, everything we've covered so far is the case for the two-moon theory. But I think the most important thing I can do in a video like this is also walk you through what we don't know yet, what science is still working on, where the honest uncertainties live. Because the unanswered questions here are not weaknesses in the story, they're invitations. The most direct gap in the evidence is compositional proof from the far side itself. The Apollo missions, all of them, landed on the near side of the moon. Every lunar sample we've physically analyzed in a laboratory comes from near-side locations. The two-moon collision model predicts that far-side samples should show a specific isotopic signature, different ratios of certain elements compared to near-side rock, reflecting the distinct origin of the collision-deposited material. But until 2024, we had no far-side samples to test this prediction. China's China 6 mission successfully retrieved samples from the moon's far side in 2024, specifically from within the South Pole Aitken Basin. Those samples are currently being analyzed. We are, right now, in the middle of getting the answer. The confirmation, or potential challenge, of the two-moon theory may arrive within the next few years, from a laboratory somewhere in China, processing rock pulled from a basin that may be the scar of an ancient moon-on-moon collision. The timing problem is a second genuine uncertainty. Models show the two-moon system could have been stable for anywhere between 10 and 100 million years, a wide range with very different implications. If the collision happened early, it coincided with Earth still being largely molten, and the effects on Earth's geological evolution would differ from a late collision that struck a more solidified planet. Pinning down the timing would sharpen the entire story considerably. The South Pole Aitken Basin's origin remains actively debated on its own terms. Some models favor it as the initial contact point of the two-moon merger. Others attribute it to an independent large impactor from the late heavy bombardment, a separate event entirely. The basin is real, enormous, and anomalous. What created it is still a live question. And the alternative hypotheses for the moon's asymmetry haven't been ruled out. The lava ocean crystallization model proposes that the near side cooled differently because it faced away from the hot young Earth under certain orbital configurations, creating asymmetric volcanic activity without any second moon required. A modified single-impact model with different fluid dynamics could, in principle, naturally produce a thicker far-side crust. These alternatives explain fewer observations with more assumptions than the two-moon model does, currently. Science changes. And that is always a feature of how it works, not a flaw. I want to say something I think is important for how we consume science content, including these videos. I am not a planetary scientist. I read papers. I try to understand them accurately and translate them faithfully. But I make mistakes. I oversimplify. If something I've said today is incomplete or gets overtaken by new research, and it will, eventually, please say so in the comments. The comment sections on these videos are genuinely some of the best conversations I have. Some of you know things I don't. I learn from those exchanges. That's not a performance of humility. It's just the truth of how this works. If you want to go deeper on any of this, the primary sources are accessible. Asfog and Jutzi's 2011 Nature paper is titled, "A Lesser Speed for the Moon's Origin from a Mars-Sized Body." It's the foundational text for the two-moon collision model. The 2023 Chen Yuan et al. Paper in Nature is titled, "Moon-Forming Impactor as a Source of Earth's Basal Mantle Anomalies." It's the LLSV-Pythia connection piece. And the China 6 sample analyses will be rolling out in the scientific literature over the coming years. Follow those papers if you want to watch science update itself in real time. What I keep coming back to, though, is this: we are the first generation of humans who can even ask these questions with scientific tools capable of answering them. Every generation before us looked at that same moon and had no idea it was the product of a collision, that it carries the geological fingerprint of a lost companion, preserved in rock for 4.5 billion years. We figured that out. In our lifetimes. Through math and simulations and seismometers and spacecraft launched to collect samples from a basin on a world 384,000 kilometers away. That, to me, is extraordinary. Which brings me to the last thing I want to leave you with. We've been talking about the past, about events billions of years ago. But the two-moon story has one more chapter. And that chapter is happening right now. The moon is moving away from Earth. Not dramatically, not in any way you'd notice in a lifetime, or 10 lifetimes. It recedes at approximately 3.8 centimeters per year. About the rate fingernails grow. But over geological time, that adds up to something significant. The mechanism is tidal friction. The moon raises tidal bulges in Earth's oceans. Earth's rotation carries those bulges slightly ahead of the moon's position in its orbit. The moon's gravity pulls backward on those bulges, which, through the elegant bookkeeping of orbital mechanics, transfers a tiny bit of Earth's rotational energy to the moon, pushing it into a slightly higher orbit. Earth's day gets very slightly longer. The moon moves very slightly further away. Year after year, for 4.5 billion years. 4.5 billion years ago, the moon was approximately 15 times closer than it is today. Imagine what that looked like. A moon filling a far greater arc of the sky, raising tides incomparably larger than anything experienced today, dominating the night with a brightness we have no modern frame of reference for. The world that existed under that close moon would have been unrecognizable, not just visually, but geologically and climatically. In approximately 600 million years, the moon will have drifted far enough away that something remarkable will no longer be possible: total solar eclipses. Right now, the moon and the sun appear identical in angular size from Earth's surface. The moon is 400 times smaller than the sun, but also 400 times closer, and those two factors cancel out with extraordinary precision. Total solar eclipses exist because of this coincidence. In 600 million years, the moon will be too small in the sky to fully cover the sun. Annular eclipses only, a ring of fire around the moon's silhouette, but never that extraordinary totality, that sudden darkness in the middle of the day, that moment when stars become visible at noon. We live in the exact sliver of geological time when the sky performs this specific miracle. A few 100 million years ago, the moon was too close and too large for total eclipses. In a few 100 million years, it will be too far and too small. We exist right now, this moment in Earth's 4.5 billion year history, when the geometry happens to align perfectly. That is not an argument for anything beyond physics. But it is an argument for paying attention. At the beginning of this video, I asked you to look at the moon and understand that what you're seeing is only half the story. Now you know the other half. What you see in the night sky is a merger. A survivor. A geological record of a collision that happened before life existed on this planet, a collision that may have made life possible. The moon is not just beautiful. It is evidence. The next time there's a full moon, look at the dark Maria on the near side, those broad, flat volcanic plains that form the face we've always known. You're looking at thin crust over a region whose volcanic history was shaped by a thick, collision-deposited far side. The next time you feel an ocean tide, you're experiencing the gravitational legacy of a merged two-moon system. And the next time you're grateful for stable seasons, for the fact that summer comes when expected and winter ends, you're benefiting, in the most indirect and extraordinary way, from a collision that occurred before there was anything alive on this planet to witness it. I've been sitting with this topic for weeks, and I genuinely don't think I'm done with it. There are threads I didn't pull on today. The connection between the moon and the origin of life in tidal pools. The role of lunar tidal heating in the evolution of Earth's early atmosphere. What a two-moon sky would have looked like to any early microbial life that might have existed right at the edge of the collision's timeframe, if any did. Some of those become future videos. We'll see. In this space documentary, we stepped back 4.5 billion years and traced the story of a world with two moons, two companions that circled this planet in the silence before life began. We followed the slow gravitational drift that brought them together. We read the geological evidence they left behind, on the moon's far side, in the deep mantle beneath our feet, in the stability of the sky above us. And we arrived at a conclusion that deserves a moment of genuine stillness. The universe we live in is not the universe we were born into. Every generation inherits a sky that is, at its deepest level, the product of violence, chance, and time. And somehow, against all probability, that specific history produced us. That will always be worth understanding. If this video changed how you think about the moon, even slightly, the next one in this series covers something that connects directly to what we discussed today, where Earth's water actually came from. Because the answer is not what you learned in school, and it traces back to the same Theia impact event that started everything we talked about here. If you're watching the moon a little differently tonight, that video is going to do the same thing to the oceans. Look up tonight. That's the only homework this video has ever assigned. Now, I know what some of you are already thinking. Is this one of those clickbait space videos? Fair. That's a completely reasonable thing to wonder, and I respect the skepticism. But stay with me for just 2 minutes. What we're going to get into today is one of the most legitimately mind-bending chapters in Earth's entire 4.5 billion year history. It is backed by real science, published in peer-reviewed journals, and the deeper you go into it, the stranger and more extraordinary it becomes. So if you're on the fence, give it 2 minutes. That's all I'm asking. The moon has been up there your entire life. Every night you've ever walked outside after dark, it was there, sometimes full and bright enough to cast shadows, sometimes a thin crescent barely visible through the clouds, sometimes hidden entirely, but always present, always pulling at the oceans, always keeping Earth's axial tilt steady enough that seasons arrive on schedule and life can plan around them. You grew up with it the way you grew up with gravity, as a given, as furniture, as the most reliable feature of the night sky. And that familiarity made it invisible in the way that only truly familiar things can be invisible. What we've spent the last hour doing together is making it visible again. Not just as a moon, but as a record. A geological diary written in ancient rock and preserved across 4.5 billion years of silence. The asymmetry between its near side and far side, that quiet difference in crustal thickness, that contrast in volcanic history, is the fingerprint of a merger. The stability of Earth's axial tilt, the rhythm of its tides, the precise geometry that makes total solar eclipses possible for exactly this sliver of geological time and no other, all of it traces back to a single event. A slow-motion collision between two moons that shared an orbit for millions of years before gravity, patient and relentless, brought them together. We didn't know this for most of human history. Every civilization that ever looked up at the moon, every poet, every navigator, every early astronomer who mapped its craters with nothing but a hand-drawn chart and a candle, they were looking at the product of a collision and had no way of knowing it. The idea that Earth once had a second moon is not ancient mythology or speculation. It is a conclusion that emerged from decades of careful science, from Apollo samples analyzed in laboratories, from computer simulations run across millions of modeled scenarios, from the work of researchers who noticed that the moon's two hemispheres simply did not add up unless something extraordinary had happened to produce them. The two-moon hypothesis, formalized and published in the early 2010s, is one of those scientific ideas that, once you hear it, makes the prior explanation feel embarrassingly incomplete. And here is the thing that I keep returning to, the thought I want to leave you with as this video ends. The second moon did not survive. It is gone in every sense that matters: no orbit, no separate body, no independent existence. But it is not absent. It is present in every piece of far-side highland crust that sits kilometers thicker than it should. It is present in a chemical gradient that planetary scientists measure when they compare samples from different regions of the lunar surface. It is present in the fact that you are here, reading or listening or watching, because the axial tilt that produced your planet's stable climate was itself a product of what that collision created. The second moon is gone. But nothing it contributed has gone anywhere. That is, when you sit with it long enough, one of the more quietly astonishing things about the universe. It destroys things completely and then hides their entire legacy inside what remains. You would never know the second moon existed just by looking at the moon tonight. But it is woven into every feature of the world you live in, at a depth that no amount of looking could reveal without the tools of science to translate what the rocks are saying. So go look at it tonight. The full disk, or the crescent, or whatever phase it happens to be wearing. Look at the dark Maria on the near side, those broad volcanic plains that have stared back at humanity across every culture and every century. Look at the edge where the near side transitions toward the far, the highlands that begin to rise as the curvature carries the surface out of view. You are looking at a merger. A geological scar. A world that absorbed another world and has been carrying that history quietly ever since. And if the video changed how you see it, even slightly, even just enough to pause for a moment the next time you step outside on a clear night, then everything we covered today did exactly what it was supposed to do. The second moon may be gone. But it turns out, it left a lot behind. The moon is still moving away from Earth at about 3.8 centimeters per year. In roughly 600 million years, it will be far enough that total solar eclipses, the kind where the moon fits so perfectly over the sun that the corona blazes into view like a ring of fire, will no longer be possible. Future inhabitants of this planet, if there are any, will look up during what their calendars call a solar eclipse and see only an annular ring, a dark disk that doesn't quite cover the star behind it. They will never experience totality. We are living, right now, in the narrow window of geological time when the geometry works. When the sizes and distances align with a precision that feels almost deliberate. That window is open because of everything that happened 4.5 billion years ago, and it is already, slowly, closing. That is the final thing the moon has to tell you. Not just that it was shaped by violence and chance and the merger of two worlds into one, but that even the story of what it created is itself temporary. The tides that drove early biochemistry will eventually weaken. The axial stabilization that made complex seasons possible will eventually require recalculation. The eclipse geometry that has made humans stop and stare at the sky in awe across every recorded civilization will eventually end. We are not at the beginning of the moon's influence on Earth. We are somewhere in the middle, close enough to the origin to still see the full inheritance, far enough along to know that the clock on all of it is running. That is the story we set out to tell at the start of this hour. It began with a sky that had 2 moons and ended with a sky that has 1, but a 1 so consequential, so structurally embedded in everything Earth became, that calling it merely a moon feels like a category error. It is a time capsule. A collision record. A stabilizer, a tide engine, and a geological witness to the most formative event in this planet's history. And somewhere in the compressed rock of its far side highlands, the second moon is still there, not as a separate world, but as mass, as chemistry, as the reason one hemisphere of the moon looks so different from the other. We came into this video with a moon we thought we knew. We leave it with a moon that has been carrying a secret for longer than complex life has existed on the planet it orbits. The secret was always visible, if you knew what the asymmetry meant. Now you do. Go find it tonight. It earned the attention. And if you have been watching this channel for any length of time, you know that we tend to end up in places like this, standing at the edge of something enormous, slightly overwhelmed, trying to hold the scale of it without dropping the thread that connects it to the ordinary world you walk around in every day. That is the whole project, really. Not to make the universe feel distant and cold and untouchable, but to make it feel like the context you are already living inside, whether you think about it or not. The moon is not background scenery. It is infrastructure. It has been running quietly in the background of every single thing that has ever lived on this planet, and the only reason we do not feel its influence the way we feel wind or gravity is that it operates on timescales too long for any one life to witness. But science can witness it. That is what makes this discipline, at its best, feel almost like a superpower. The ability to read time in rock. To hear a collision in a chemical ratio. To look at a hemisphere of terrain that is statistically thicker than the other and reverse engineer, from that single asymmetry, the existence of an entire second world that has not existed for 4 billion years. That is not a small thing. That is humanity doing something genuinely extraordinary with the tools of careful observation and accumulated knowledge, and it deserves to be treated as the remarkable achievement it is. So the next time someone tells you that science is dry, or that space documentaries are just pretty pictures with dramatic music, and I will admit, sometimes the music is a lot, remind them that the moon they see every night is a merger. That the stability of the seasons they take for granted was purchased by a slow-motion collision between 2 sibling worlds sharing an orbit. That the tides pulling at every ocean on Earth right now are the echo of an event that happened before the first bacterium ever divided. The universe is not background. It is biography. And we are only now, in the long arc of human history, beginning to learn how to read it. That is what we came here for today. And that is exactly what the second moon, against all odds, managed to leave behind, a reason to keep looking up, and a reason to keep asking what you are actually seeing when you do. So the next time you step outside on a clear night and the moon is up, full and bright, or just a sliver catching the last of the sunlight, take 1 extra second before you look away. Not to think about tidal locking or crustal asymmetry or Trojan orbit resonance, though all of that is in there. Just to register that you are looking at a survivor. A world that took a hit that should have erased it, that absorbed another world entirely, that carried the consequences of that merger across 4 billion years of geological time, and that is still up there, still drifting outward at 3.8 centimeters per year, still pulling at the oceans, still holding Earth's axial tilt inside a range that makes complex seasons possible, still doing the quiet infrastructure work that your existence depends on without asking anything in return. That is not background scenery. That is the most consequential object in the night sky, and it has been trying to tell you its history the entire time. The story we walked through today, from the chaotic early solar system to Thea's slow drift toward Earth, from the violence of the giant impact to the merger that built the moon's asymmetry, from the tides that may have seeded life in shallow coastal pools to the axial stability that let complex ecosystems develop across hundreds of millions of years, that story is not finished. The moon is still moving. The tides are still running. The far-side highlands are still waiting for a lander that can drill deep enough to read the full chemical record of what got buried there. And somewhere in the next decade or two, if the science keeps moving at the pace it has been, we will know more about the second moon than we do today. We will have a sharper picture of its size, its composition, the exact geometry of how it merged. The asymmetry will stop being a mystery and start being a confirmed chapter in a story we can finally read end to end. And when that happens, the moon you look up at tonight will make even more sense than it does right now, which is already, if you have spent the last hour here with us, considerably more sense than it made before. We journeyed into something enormous today. The kind of enormous that does not announce itself but just quietly sits inside the data, inside the rock ratios and the crustal thickness measurements and the orbital resonance models, waiting for someone to notice that the numbers are pointing at a world that used to exist. We noticed. And now you cannot unnotice it either, which is arguably the best possible outcome for a space documentary about a moon collision that happened before anything alive on Earth existed to see it. Go find the second moon tonight. It is wearing the face of the first.